So remember that periodic trends have to do with predicting sort of like whether they're increasing or decreasing as you move in one direction or another on a periodic table. So the first periodic trend that I'm going to talk about is atomic size. They will sometimes call this atomic radius. Okay, so you know metallic character, we learned in the last section. And then here we're talking about atomic size or atomic radius. If I'm talking about two nonmetals attached to each other, and I take the distance between their nuclei and I divide it in half, that's a covalent radius. So an example of that would be here. I've got two chlorines attached, take the distance between their nuclei, divide it by 2. That's my covalent radius. Metallic radius is simply if I'm looking at the identical nuclei of two metal atoms adjacent to each other in a crystal structure. An example would be right here with these two sodium atoms. Take the distance between the two sodium atoms, divide it by 2. That's called the metallic radius. Okay? They're just terms. I'm never going to talk about them after this. Okay? On the next page, they go over the things that influence metallic radius and its trend on the periodic table. So they give you an image of what the atomic radius looks like on the periodic table, but let's go over these factors first, and then I'll explain a little bit more. So there are 2 factors that influence atomic size. Okay, the first one is the number of energy levels present. So that means we're talking about the Ns, okay? So as the number of Ns increase, meaning as you go down a group on the periodic table, the outer electrons will be further and further from the nucleus, so the atoms will become larger. So that means if I take a look, can I move this down to the image? Okay, so if you take a look down here, so this would be n equals 1, and this would be n equals 2, and so on. So for n equals 1, I've got my 1 shell, and that's where my valence electrons would be. For n equals 2, I've got 1, 2 shells. For n equals 3, I have 1, 2, 3 shells. Obviously, the more principal energy levels or Ns that you have, the further and further away the outermost electrons will be from the nucleus, and that will cause the atom to get larger. Part of the reason why the atom is going to get larger is not only because you have extra Ns, but because the electrons that are in this outermost shell, they're not able to feel that positive charge from the nucleus as well. So therefore, the protons can't pull in those valence electrons as well, and your atom gets larger and larger. This is known as the effective nuclear charge. Okay. The other factor that you also have to consider is these inner Ns, since they also contain electrons, will repel each other, and that will cause the atom to get larger. Okay? Now, in terms of the second factor that influences atomic radius, the amount of nuclear charge, meaning the proton pull that they feel from the nucleus, the valence electrons in the outermost shell cannot feel that as strongly as the number of Ns increases. So this is called the effective nuclear charge. The effective nuclear charge will increase left to right across a period. Okay? That's because I'm adding more and more protons. Okay? At the same time, as you move left to right, you will put electrons in the exact same N. So that means that those electrons will feel that nuclear charge or that pull from the protons more and more as you move from left to right, and your atomic radius will decrease. Okay? Effective nuclear charge is often abbreviated as ZEFF. So let's take a look at the image of the atomic radii in the picture down below. So as we come down here, you may notice that the atomic radius decreases, like in this n equals 3, it's a lot easier to see because my atomic radius is getting smaller left to right, as is the number of protons, right? So I've got 11 protons here, 12 protons here, 13 protons, okay? You get the idea. So I'm increasing the positive charge in the nucleus, but at the same time, you're adding electrons to the same outermost shell. So like here we've got 3 ends. So if you keep adding electrons to the same shell, and then you keep increasing the positive charge in the nucleus, it has the ability to pull those electrons in and then make your atomic radius smaller. Here where I have my transition metals, you'll notice in the transition metal region, it appears like the atomic radius isn't changing that much. You're right. And that has to do with the electrons that are going into the d orbitals. Okay. What I would concern yourself with are adding ends as you go down a group, and then the effective nuclear charge increasing left to right, which is going to pull in those electrons and make the atomic radius smaller. So atomic radius will increase in this direction and this direction. On your periodic table, which is the exact same trend as metallic character. Okay, I would recommend reading this part about atomic radius because it's really insightful and it explains it really, really well. Okay? All right, let's move on to the next figure. Okay, this next figure right here is simply showing you that as the atomic number is increasing and as we move period by period, you can see a different trend, right, in the atomic radius. So generally speaking, the alkali metals are the peaks, and then your noble gases are the troughs, and that's because the alkali metals would have the largest atomic radius in a period, and the noble gases would be the smallest atomic radius, okay? And then we can take a look at the next section when you guys are ready. Okay, now, in addition to what we just talked about in terms of the trend for atomic radius, if you are looking at ions, you need to consider how many protons and electrons are present. So here they've given us a list of ions from an aluminum ion over to an oxygen ion, and some of them are neutral, like neon is neutral, and they want us to rank them in order of size, from largest to smallest. So what this means is look at the subatomic particles. So here if you take a look at nitrogen, nitrogen has got 7 protons. So I'm going to list the protons on the top and the electrons on the bottom. So nitrogen has 7 protons. The -3 charge means it gains 3 electrons. So this has 10 electrons. And then oxygen has got 8 protons with 10 electrons. Fluorine has 9 protons with 10 electrons. Neon, 10 protons, 10 electrons. Na+1, 11 protons, 10 electrons. Mg+2 is 12 protons, 10 electrons. And then aluminum has got 13 protons and 10 electrons. Okay, so here you can see that the largest atom, this is the largest atomic radius. Okay, this one has got the fewest protons, which makes sense because it doesn't have as much of an effective nuclear charge or positive charge in the nucleus to pull in all those electrons to make it smaller. Whereas over here, this Al+3 has got the smallest atomic radius because of the fact that it has got the most protons in the nucleus, so it is able to pull in those electrons and make the atom smaller, okay? Now, a common question that you might get is comparing cations with its neutral atom or an anion with its neutral atom. So here it says cations are usually smaller than their neutral atoms, and anions are usually larger than their neutral atoms. Why is that? Well, if you've got something like Li plus 1 versus Li, Li plus 1 has got 3 protons and 2 electrons. Neutral lithium has 3 protons and 3 electrons. Okay, so this lithium ion will be smaller than the neutral lithium because there's fewer electrons, so this positive charge of the nucleus dominates and it sucks those electrons in closer. If I'm looking at something like O negative 2 versus O negative 2 has got 8 protons and 10 electrons versus this one has 8 protons and 8 electrons. Here, the negative charge dominates because I have more of it, so that means that this would be a larger atom and this would be a smaller atom. Okay, so those protons in the nucleus can't pull in the extra electrons, and that makes it larger. Okay, we've got 2 other trends to talk about, and then we're done. So let's talk about ionization energy. Okay, ionization energy is often abbreviated as IE. It's the minimum energy that it takes to remove an electron from something in the gaseous state or an ion. And depending upon the number of electrons that we are removing, the first electron that you remove is known as the first ionization energy, and it's denoted as IE sub 1. Generally, a neutral atom will become a positive 1 cation. This is the generic equation for what it looks like. This is the energy that you put in to remove that 1 electron. This is that 1 electron leaving. And then this right here is the cation that you form when you remove that 1 electron. Ionization energy tells us how strongly an atom will hold on to its valence electrons. It's really important to know because a low first ionization energy tells us that something will likely lose electrons and form a cation when a chemical change happens, okay? If you have a high first ionization energy, that means that element would rather gain electrons and form an anion if it wants to form an anion at all, okay? Smaller atoms holds on to their electrons more strongly, so therefore they're probably going to have a higher first ionization energy than something else. But generally speaking, as the atomic size decreases, your ionization energy should increase. So your trend would be ionization energy increases in the opposite direction of metallic character and atomic radius. So it increases up and to the right. Okay, so let's take a look at the next page. This graph gives you something similar to what we saw before. The only difference is that this is for ionization energy. Here, the peaks are your noble gases. The troughs are the alkali metals. So you can tell, I shouldn't have shaded that one. You can tell here that as you move from left to right, your ionization energy is increasing. Okay, and that's because the noble gases will be the smaller atoms in a period. The alkali metals will be the larger atoms. So it's going to take less energy to remove an electron from an alkali metal than it will to remove an electron from a noble gas, because the smaller atoms have their electrons closer to the nucleus, and that's why it would take more energy to pull it off. Okay.